Hi, Physics 1. This is Mr. Janowski. This is Chapter 6, Homework 2, Problem 1. So what we have here is a man with a mass of 82 kilograms standing on a bathroom scale in an elevator, as you do. The elevator is accelerating downwards at 1.70 meters per second squared. What does the scale read in newtons? And there is our answer there, and we've got to figure out how to get to that answer. So, first things first, as always, we're going to do a step, huh? So the question is, what does the scale read in newtons? So what do scales read? Scales actually read normal force. We commonly like to think that scales read weight. That's sometimes true. That's usually true in practice. But in general, scales read normal force. So remember that when you're doing these problems, that scales read normal force. So that's what we're looking for. It's a force. It will be in newtons. So what do we do from there? We do a step 1 all year long. Step 1 is make a sketch. So in our sketch, what have we got? We've got an elevator. We've got a scale. We've got a man standing on the scale. And we can assume there's some kind of cable on this elevator going like that. Let's see. The elevator is accelerating downwards at 1.70 meters per second squared. So I'll write it like that. I know it's downwards, so maybe it should be negative, but I'm not going to do it that way. I'm going to write it as a positive number. I will remember that it's downwards by having this downwards arrow right there. And the other thing we know is that this guy's mass is 82.0 kilograms. So that's what we've got. So that's step 1. Step 2 in a force problem is free body diagram. So what is a free body diagram? It's like a sketch, but it's not exactly a sketch. So in this rather particular kind of sketch, we are going to turn the man into a box. So our man is now a box. The only thing we attach to this box are forces. No accelerations, no masses, no velocities, nothing else, only forces. So what forces are acting on this man? Well, we have his weight, which will be going down. So that's F sub g is his weight. And I'll do a little bit further. All right, F sub g is equal to mg, because that's what that is. And the other force we have is a normal force going up. So the man is in contact with the scale. So that means the scale is providing a normal force on the man. So that's what we've got. Now, those are our only forces in this problem, and we're not attaching anything else because in step 2, in the free body diagram, FBD, you only attach forces. On to step 3. So step 3 in a force problem is to write Newton's second law. This is the most important thing you will learn in physics all year, so you will write it. So F equals ma. But in this context, we've got to be a little more specific. We're going to write this as sigma F equals ma. And when we write this down, we want to remember that force is a vector and acceleration is a vector. So we put the hats on the things. So now these things have hats. Now the next thing we're going to do from here is turn the sigma F, the sum of the forces, into the sum of the forces. So what does that mean? That means go back to step 2, grab all of your forces. So I've got Fn and Fg. We're going to grab all of our forces. We're going to plus them together because this is sigma. Sigma means sum, so we're going to plus them together. And in step 3, all of our vectors continue to wear hats. So that's how we do step 3. We have that. And on the right side, we keep mass times acceleration with an A with a hat. So we've got that. On to step 4. I'll go with blue for step 4. Now I'll go with black. So step 4 is the math. So in a force problem, the first part of the math is to take the hats off of your vectors and put in the signs. So we're going to take the hat off of F sub n, the normal force. And what sign do we put in with that? Well, it's going up, so that gets a positive. So, plus F sub n, but of course you don't really write that plus. It's just assumed. So that's positive. Then we get to F sub g. Well, that's going down, so that gets a minus. So minus f sub g like that is equal to ma. Okay, now a is a vector, so when we take the hat off of that, we have to think of its sign. And in this case, a is going downwards, which is there. Well, I also have it here. I told you this is how I'd remember. So in the sketch, I've got the downwards arrow. So when I take the hat off, I put in a minus sign. So remember, this is not m minus a. This is m times minus a. So I'm going to rewrite that as minus ma. You're not subtracting acceleration from mass. You're not allowed to do that. I'm writing it as that. So at this point, let me just rewrite this quickly. What we've got is f sub n minus f sub g is equal to minus ma. Now, the name of the game, remember step ha, is we're trying to solve for normal force. So I've got to get normal force by itself. So I'm going to add f sub g to both sides, which will give me f sub n is equal to minus ma plus f sub g. Okay, m is a number, a is a number. I know those numbers. F sub g, what am I going to do with that? Well, look down at the bottom. F sub g is equal to mg. So I replace this with this. Okay. If you wanted to, you could, factor out an m. You could end up with something like this. M times minus a plus g. You can do it that way if you want. I'm not going to bother. Well, I have bothered, but I'm not going to bother. At this point, I'm just going to go in the numbers. It's not so much work in this case to just do the numbers. So minus m. M is 82.0 kilograms times a. A, remember, is 1.70 meters. I'm sorry, meters per second squared. Here's the thing. A is down. Do I put in a minus here? I don't. I already handled the minus at this point right here. So that's when I made it minus. That's when I handled the downness of A. So I don't need to do it again. That minus out in front is doing that job for me. So I'm getting rid of that. So we have that. And then this is plus M, which is still 82.0 kilograms, times G. And remember, in this chapter, G is the positive number. So that is 9.8 meters per second squared. So same thinking. Well, how is G a positive number? Isn't gravity down? Well, yes, gravity is down, but we've already accounted for the downness of the gravity right at this point. When we took the hat off of F sub G, that's when we made gravity down. So we did it once. You don't want to accidentally do it twice because then that would be a double negative. You'd make it a positive. So yeah, that's when we did it. We did all of that. If I do all this together, I mean, certainly if you're good enough in the calculator, you would do this all in one shot. But if we do this, what do we end up with? This first term ends up being minus 139.4 newtons, plus this guy over here ends up being 803.6 newtons. And then you do that little bit of math, and you end up with F sub n is equal to 664.2 newtons. So you've got that. You put a box around it, so your physics teacher knows that you're done. It's not going to do that with a turbo box. I'm getting distracted and not writing very clearly. Okay, so we have that. And now we do step Always do step Okay. First of all, did we solve for the right thing? Did we give it the right units? Yes. Normal force, units are newtons. Is this a sensible number? That's a little harder in this case. There's no bloody cheetah kind of trick for this, where like, oh, double it, now you know miles per hour, this is a sensible velocity. That doesn't work for this. We're just not used to measuring things in newtons. So you don't have very much experience in terms of your day-to-day life in measuring forces in newtons. So you just have to trust me that this is a sensible answer for a normal force. So yeah, there you go. The normal force ends up being 664.2 newtons. So hopefully you found that helpful.